polymorphism.
Okay. So I gave the talk subtitle, Unsettling Value Restriction, and recently this subtitle got whole new meaning, unfortunately. Well, value restriction, as we know, is implemented in all the languages, and it has been mentioned already, was introduced by this paper by Andy Wright in 1995, and in 1997, and it was made to standard ML and using OCaml. Yesterday I was talking to Peter Thiemann, and he relayed to me rather sad news. Well, you can see that, and it happened just a week ago, on Friday, actually less than a week ago. Well, so he has many contributions, and value restriction is one of that's known, and I hope that this work will, remind you again about these contributions. Well, this talk is about, well, it started as a practical talk. It's providing a way of implementing stage languages and implementing quotation and stage languages. So one of them is this source-to-source preprocessor, it has two features, and supports polymorphic. So what makes the things a little bit interesting is that, well, you might remember 2 years ago I gave a talk at exactly this workshop in Boston, and I was giving a talk about implementing MetaOCaml, and in passing in the middle of the talk I mentioned exactly this method, source-to-source translation. And 2 years ago, and at that time I said, yes, it's a good method, it works, I know it's very simple to implement, has many advantages, but it just cannot support polymorphic letters. There's no way, no how. It just cannot work. And here I am, 2 years later, standing here at the same workshop, and say that, well, it actually does work. So it means that, yes, you can translate this code to OCaml, and it type checks, and it produces exactly the same code that it works. So it does work in practice, it really works. And it almost works in theory. And by what do I mean that it works in theory? Well, there are kind of two things, is that there are some theoretical problems to justify. I need to justify why it actually works and how it works. And I kind of wave my hands and go through this, justify how it works, and I will try to wave my hands here. But of course that, some proofs are required and so forth. And also when I'm waving my hands, I will wave away many very interesting, fascinating details that should be actually looked at. And this is actually more interesting part of the talk. It's not the one that, yes, it works in practice, but getting it works in theory is by far more interesting challenge. And it leads to, I believe, to re-examination of all this work that led to value restriction, because it's also, this application provides a compelling application why we need to go way beyond even the relaxed value restriction once implemented OCaml, but definitely beyond the value restriction. But first to remind you where we stand. So this is a slide from 2 years ago, and I remind you where, why I believe that the problem is important and how we came about. So this, actually it's on all the slides. So we're talking about staging. We're talking, it's a talk from a MetaOCaml, implementing MetaOCaml. So it would be a few MetaOCaml things. But what we want to, the goal of MetaOCaml is to write programs that generate programs, and time-honored way of doing this is using quotation. It's this list. Well, in OCaml, in list, you have quotations like those, and quotes, and OCaml we call them brackets, and so if you take the expression and enclose on a quote, then it becomes a value. So it represents this expression, and you can also think about it as a generator. So it eventually would generate this expression. But as far as MetaOCaml is concerned, is a value, it's a type of value. And you can pass it around as any other value, and you can splice it into some other value. And that's what it's called. There are some more constructs, but I'm not going to talk. That's also all slides, and there are 2 points about them. As you can see, you can even quote variables. So the quotations can be open. And it's also quotations in OCaml, MetaOCaml, unlike quotations in Lisp, they're actually hygienic. Okay, so 2 years ago I said there is a wonderful method of implementing staging by just translating it away. So that's in the, on the top line. Here's, for example, here's code, and it contains quotations. And how we implement it, we write a preprocessor that translates this code into this. And it includes certain things like lam, add, mul, int, and so forth, and these are code-generating combinations. But for example, int takes an integer and generates code to represent this integer. And add takes 2 pieces of code to represent some things and creates a code that represents additions. And there are, of course, more combinators. You can kind of see how it goes. One of the interesting things about this translation, you can see there is a bindings in the meta level, like this one, or in the object level. So there's the bindings in the generators. And here it became, why? It became the bindings in the object language. So the binders in the meta language become, object language bindings become meta language bindings. And this is a very important property, and also, you know, if you do, write things further, then it guarantees hygiene for you. And it also makes it easy to work with. But we'll remember all that. So, it has a very interesting, very good implications because it's source-to-source translation. You just write a preprocessor from MetaOCaml, generate OCaml, and afterwards you just forget the staging ever existed. So it becomes standard OCaml code, and you can do anything you want. It's a very good thing because then you can use all the OCaml infrastructure. You don't have to touch the base compiler. You can use all the libraries. You can use IDEs. You can use everything. So it's a wonderful thing. And another wonderful thing that the typing is preserved. So if you translate and then type check, and if the code type checks, it means the original MetaOCaml code, the ones in the code, also type checks. And so the generated code would also type check. And conversely, so if after the translation it would be a type error, it means the MetaOCaml code also was ill typed. So it's a bidirectional correspondence. The typing is preserved. And you don't have to write your type checker for quotes because it's OCaml type checker does everything. So it's a real wonderful program. And it does work. And well, we heard a talk from LMS about lightweight modular staging in Scala, which actually does implement exactly this idea. And they had great success with this approach. Well, of course, there are some complications. For example, I didn't talk about, this was a very simple example on the lambdas and applications, but in real language we have loops, conditionals, and other stuff. Well, we can deal with this, introduce stacks. There are, of course, other things. Well, what about pattern matching, for example, and, well, type annotations and so forth? Well, there's, complications, then you have to do something, but that we know what needs to be done, and there's a paper Scala virtualize, and I go into great details what you actually need to do to implement all the things. So it's all, complex but doable. But there is this thing. Let polymorphism. So, and this is, I claim, failure. And how Scala does away with this, actually asked PR 2 years ago, and he said, well, we just, in our embedded languages, we just don't generate polymorphic letters. So they don't have any problems. But if I am going to implement MetaOCaml and the way it occurs, that I actually wanted to implement. So it just doesn't work, and that's why I said that for that reason, I cannot use it in MetaOCaml, and for that reason, MetaOCaml is not a library for OCaml, it's actually a fork of OCaml, and it has to do go into a type checker and modify the type checker and so on. So that's the source of all the problems. So let's look more carefully at where the problem comes in. So here's well, let's forget about these quotes and consider the just OCaml expression. So we have a L binder of empty list, and then we add, so prepend one or prepend a pair of elements. And it can only work if L is actually polymorphic, has a polymorphic type. And it is indeed in OCaml as a polymorphic type because empty list is a polymorphic and a polymorphic value. And let bindings to polymorphic values we generate. So if it indeed works. Well, let's imagine how we're going to translate it. So that's, how translation could possibly look like. If we assume this combinator let, which is kind of, well, mixture of both up and down, right? So that's how the translation works. Well, unfortunately, as you can see, this translation does not type check. Why? Well, because we saw the property that the bindings L in object level becomes in the translation of bindings in the meta level. So here it is, binding in the meta level. Right? And lambda bindings in Hindemiller type system is not polymorphic, right? So here L cannot be polymorphic, therefore that expression cannot touch. Well, you can say what first class polymorphism? Well, if you, first, not all languages have first class polymorphism, and the one they have, they insist on type annotations. And to give the type annotation, we have to type check. And it's actually exactly what we want to avoid, right? So it just doesn't work. So that was the problem. And that's the actually slide. I think it was 2 years ago. That's how we start this thing. We just have to abandon the whole thing and do something else. Well, and then I thought about magic. Well, let's imagine, hypothetically, this kind of magical thing, generalize, intended to be used like this. So if you write this generator, then it kind of should generate this code. And the way it goes about it, so here's this expression, and it kind of puts this let outside where new scope is. Generate this expression, generates let, keep bindings to fresh variable t, and replaces itself with this binding switch. So, if we have this combinator, then we can design a new translation. So this combinator isn't meant actually for the end users. It's meant to be used only in translation. And here's a new translation in the top line. And here how it works. So if we have this expression that gave us the trouble before, we translate it into this way. So, and it now type checks. Why does it type check? Well, there's a property of this translation. It also translates the binding in the object language into the binding in the meta language. But now the bindings in the object language became let binding in the meta language. And let bindings are generalizable. And not only they're generalizable, they're actually generalized. Although you say it shouldn't be happening because this is an expression, this is not a value. But fortunately, Jacques implemented relaxed value restriction, and if this value has a polymorphic type and a covariance, and this is the case. So yes, that worked. So, and this genlet is, not actually really magic. It has been known in partial evaluation community for many years, and this implementation is very simple, so it just fits into a couple of lines. I'm not saying that explanation fits into a couple of lines, so, and I don't have even time to, after rest of my talk, so I just skip it. So, is this it? So, all the problems solved? Well, look at a more interesting example. Here, very kind of similar, now we have a polymorphic identity. So if you have function alpha to alpha, so if you look at our common code, then it should work, right? Because f applied to integer, f applied to pair of integers, and it's a polymorphic identity function, and it should work. So here's this translation using this magic genlet, and now it does not type check. So why does it not type check? Well, the reason is because this expression has the type alpha to alpha code, right? And alpha here appears in non-variant position, right? It's not a covariant position. So that's why it's not actually. Well, instead of talking, that's a technical reason, but let's look at intuitive reason. Why, we don't want this, generalized. Again, forget about codes. So this is expression where R set is the function that reads a value from the reference cells and writes another value in the reference cell, right? So it writes one value that is given and returns the previous value from the reference cell. So if you use it in this translation, we don't want to back check this code, right? Because in this case, it will put in the reference cell integer and a pair. But if we close the translation and translate it, and if we say, well, let's generalize, non-covariant, non-variant types, then this code would type check, and we really don't want it. Right? So there's a good reason that we don't want to type check the things. Well, so what we're going to do, Well, we put the value restriction to a whole new level. So now when we perform the source-to-source translation, we have to recognize that, well, we are dealing binding to a value, syntactical value, for example, functional value. And in that case, our translation should use not the regular generate, but this new generate file, which has this particular type. And for this type, it uses not a regular arrow, but this my type arrow. And by this type, as you can see, by fight, I declare it to be covalent. And in that case, OCaml will happen. So, is this it? Well, it's not quite it yet. There is still one case, one edge case, where this translation, this generalization is unsound. And it actually has to do exactly with this example, which I said, but in a somewhat different way. So this example occurs maybe through the talk 3 times. So if it occurs on the level of OCaml, we don't want to generalize, right? And this has been a problem since the 70s when ML was designed. Now I put it in a bracket, and this presented a problem, and that's how I'm trying to deal with this. But if we try to put brackets a little bit different way, using cross-stage persistence, then it's again a problem. So this interesting example shows up 3 times. But my conjecture is that this example, which is like dealing with cross-stage persistence, is that it's a rare edge case, and it's the only rare edge case that for this generalize. And so if we somehow, and it's actually very easy to deal with. So if we manage to deal with this case, then this get let one is solved, and this can proceed. So that's my conjecture. And so that's where we stand now. So what's left to do? So what is the research problem? So first of all these things that I said, I can wave hands why it should be, it should be working. And of course, we need some proofs as to why indeed it actually works. And there is a different reason. So I talked about these interfaces, but I never talked how they actually implement it, right? So how exactly generate implement it. But here is a very simple implementation. That's alpha code is actually thunk, right? And this int unit is create thunks and add create thunks. And now if we apply this implementation, then all of a sudden we are not talking about staging anymore. We are back into standard, old standard OCaml. So everything that I talk now is actually applicable to OCaml direct. Right? So all the problems that I said, they all appear in OCaml. And now we actually can solve them in OCaml. And now we need to have some kind of more relaxed value restriction. So the program is, what do we need to do to get code upon this translation, upon this interpretation of code coming into that check and and of course, there is another thing to this. Well, we actually wanted to implement it. Now there is a viable way of implementing that OCaml, and it requires some effort to do it. So there are some problems, but technical problems, but we actually have to do it. Well, and this is the end of my talk. And so if you're interested in this research program, well, talk to me, read the papers and so forth. And what I wanted to, the last line is that there is as you can see, that there is kind of impression that we solved the polymorphism problem with lead binding to solve. So there are more things to it than this side. So maybe it's time to revisit this. Here's that staging, and these are very compelling. Yes, Francois.
The gen length combinator that you showed does 2 things. It translates the lead to a lead, and it hoists the lead binder. But the hoisting feature was not really needed here, was it?
Well, it is needed because, well, it's... It actually is needed because just for for very short step. Because, well, I mean, like in here, right? So, I mean, we wanted to generate letters here. So we can't, I mean, put let, I mean, so it has to appear somewhere outside, right outside the expression. But if it were not hosting it, let would be embedded in this clause, and what you don't want to do is, right? So it has to be kind of, it has to, this is the binding, so it kind of has to go outside. Yes?
So you identify this problem with functions.
Yeah.
And you kind of claim that you think that functions are the only
Well, no, I probably, I mean, shouldn't give this impression. Yes, I mean, there are other polymorphic values, right? There's, well, in here in the talk, there's two, empty list and functions.
Right.
Well, empty list, I mean, on easy, so all the covariants, they're all, I mean, solved once and for all. We don't even need to think about it, right? So we have to think about which are non-variant or contravariant, right, which is functions. So functions the most, well represented and understood way, but could be other values of the things.
So I guess my comment was people have invested the time into the covariance,
Yeah.
covariance, and relaxed value restriction,
Yes.
and not just sort of said, well, we'll just do something special for functions.
Okay.
So maybe, maybe the literature on why, we go to that effort and not just special case functions might also reveal some other cases.
Yes.
Where there are covariant, data types that people really do want to use, that might.
Yes, I agree. I mean, I couldn't think about offhand, I mean, what
But it seems like with this, does this approach basically work for anything like that? Anytime you get this covariance, just.
if the covariance is automatically, so everything works. It's, I mean, Zach is already, I mean, so with covariance, they have a good story. When there is not covariance, then of course we have to look at case-by-case basis, unless we have a theory that says how to deal with non-covariant. And I don't think that we even have this theory how to deal with non-covariance. So functions are a good, important case that maybe we just start with them and then see if we can, I mean, go further. Yes?
So that kind of raises a question where, so you have this cost type,
Yes.
which is expressions, but in some sense you want this kind of sub-grammar, which is values, and that has a vowel one as well, which looks at the covariant notation. And then when you translate values, you translate it into that one.
Yeah, it could be, it might have been, I mean, I haven't looked at, I mean, how complex the type system would become. Right.
The translation would probably.
Yes, yeah, it could be, I mean, but you also need syntactic test for it, right? So, I mean,
Right.
because, so,
So you could do
yeah.
a syntactic test.
yeah, it could be. Yes.
Generalize, you maybe with some kind of delayed control.
Yeah.
Does the type problem you try to generalize here in your shifts on the type of shift?
Well,
Sorry about that.
no, yeah, I mean, no, in a sense, I mean, no, it does, but, where is so the type to the prompt is the answer type, right? But, I mean, yes, I mean, here it is. That would be right. That's where.
Maybe it's under
Well, fun case, there, I mean, binding with continuations, right?
but it doesn't have a D, right?
Yeah. Well, I mean, here
With
then.
the binder.
Yeah,